right. Same stuff, different day, right? You've got a lab report that you're going to have to turn in, a homework assignment that you're going to have to do. Both of those are Tuesday, the 28th of October. I didn't put it down here on the slides, but I'll make the announcement that a week from today, next Thursday, we won't actually be meeting together as a class. That lecture will be posted online because I'm going to be traveling down to Clemson to work on the FE exam. So I won't be here, we won't meet, but you'll still have a class.
That Thursday?
Yeah. Next Thursday, I think it's the 30th, October 30th. No class. No class meeting. We'll still have a class lecture, and I'll post the recording link on MU Online along with all the rest. And I'll tell you that we will have a quiz the following Tuesday just to see if you watched the lecture and give you some incentive to not accidentally miss that one. All right. Any questions related to the announcements? We're going to start on Chapter 5 today. Now, I told you that Chapter 4 in many ways was kind of like the pinnacle of the course. Like so many of the big ideas were presented in Chapter 4. Bernoulli's equation, rotational flow, different types of acceleration, Euler's equation. Those were, Chapter 4 was loaded with really important stuff. Chapter 5 is also really important not just for fluid mechanics problems, but also for environmental engineering and a lot of the water resources applications that come in future water-related classes. And so Chapter 5 is also pretty important, and there's going to be different combinations of principles from Chapter 4 that will be combined with things from Chapter 5 to come up with interesting combo-type problems. So it's going to start to get a little more complicated and interesting, though nothing to be intimidated or scared by. It's just that we're going to have combo problems where you have to remember one chapter and integrate it with what is included in the next chapter. All right. I don't think that we talked about this key idea slide that I had provided in the last lecture, but we didn't get to the last slide of the lecture. So on the homework assignment you've got due on Tuesday, problem 51, there is a piezometer that's connected to a pipe that has a contracting section. And we've talked about this extensively, and you've seen it in the lab, that a contracting section increases the velocity. So where the pipe diameter is wide, the velocity is 10 feet per second. And the velocity here at the contracted section isn't known because they haven't told us the pipe diameters. If they'd said what the diameters was, then we could just measure that velocity directly. But instead of that, we have piezometers that's measuring the piezometric pressure at both of the locations. Now, what would the water levels be if there was no water flowing through this pipe? If it was just static conditions, would there be a deflection like that? No. The deflection is only because water is flowing. If it was static in both the piezometers and in the pipe, then the water levels would be the same. So the fact that it's deflected tells us that the water is moving. So the pressure here at the wide section is bigger than the pressure at the throat. And how do we know the pressure is bigger? The pressure is higher at this location 1 than it is at location 2. It's because the water level rises higher in that piezometer. These piezometers are an indication of how much pressure there is at a certain location. And so the process here is to combine the measured value, the measured deflection between the two, along with the definition of piezometric pressure into Bernoulli's equation. So you're going to group terms together in the same way that we did in the last class's example problem, where we'll have P1 plus gamma Z1, and then if you take P2 and gamma Z2 to the left side of the equation, that's going to be PZ1 minus PZ2. And so you can just substitute in gamma delta H for those terms, and there will be no other unknowns besides V2. V2 will be the only unknown in here, in the Bernoulli's equation, V2 is the only unknown if you substitute in what the piezometers tell us about piezometric pressure change. So that's some of the key ideas you'll need to solve problem 51. All right. Here's an aerial photo of the fourth largest artificial reservoir in the United States. It's the Oahe Dam and the Oahe Reservoir. It's in South Dakota. Actually, the reservoir stretches actually more than 100 miles up the river. It sort of dams and pools a couple of rivers that converge together for quite a long distance, and it has a storage volume of 23 million acre feet. And we talk about units a lot in this class, but we haven't talked about an acre foot yet. What do you suppose an acre foot is measuring? Foot is a unit of length. What's an acre? It's area. So if you multiply length by area, what does that give you? Volume. So this is a measurement of volume, and what it says is if you had 23 million acres of area and there was 1 foot depth of water over that 23 million acres, that's how much water is in this artificial reservoir. So this reservoir isn't 1 foot deep everywhere. You know, some places, like probably right at the dam, it's maybe 40 or 50 feet deep. You know, near the end of one of these little inlets here, it's probably just a few feet deep by the shore. So if you integrate the many different depths and consider the entire area of the reservoir, it's saying that the volume of that's 23 million acre feet. It's owned by the Army Corps of Engineers, and this project was developed both to generate electricity, and it generates enough power for most of the north-central United States. All through South Dakota, North Dakota, a lot of people use the power that's generated at this dam. But it also has other benefits as well, namely flood protection. If the Missouri River at this location wasn't dammed, then downstream they'd have a lot more flooding, and flooding would occur more regularly. And so a big part of this dam's justification was the annual benefits that would be provided in terms of flood control to agriculture and to also residential areas in the floodplain. So it's an interesting case, and the reason why I bring it up is that the principles related to control volume analysis come into play for reservoirs like this. You've got water coming out here at the dam, out of the reservoir. How else is water leaving the reservoir? I can think of, besides water coming out of the dam, 2 other really big ways that water exits this reservoir. Can you think of some ideas? Evaporation is one of the 2, right? And so on warm, sunny days, especially if it's windy, then the sun's energy will vaporize some of this liquid, and it gets up into the atmosphere. And actually, we just finished talking about evaporation in the hydrologic engineering class, and it's a really complicated thing to try and estimate how quickly water is evaporating from a liquid surface like this. So one of the 2 ways water leaves the reservoir, besides the outlet, is evaporation. Can you think of another place where the water's going? Yep, it's going into the ground. So it's infiltrating, seeping into the ground. And so it's going straight down, and it's also seeping outwards. Here's a close-up of the dam itself and some of the hydraulic structures they've built along with the dam. You can see here's the intake. The water that's going through the outlet, it's not like they just put a pipe right next to the soil on the dam. Do you have an idea of why they would want the inlet not like right up, like a big pipe right at the face? That's exactly it. Yeah, if you've got the water going into that pipe at a really fast rate, then it could scour, because if we are going to draw, here's the dam. The problem with having a pipe that was going and the water spraying out like this is that the water would be entering from lots of different directions, and here's the water level. It could possibly be coming across the face of that surface and creating sediment transport, which obviously is bad for safety. You don't want the dam to fail because the material was scoured. So what they do instead is they just have a pipe sticking out into the lake. The intake that way doesn't cause any sort of disturbance along the surface of the dam. There's a tunnel, an underground tunnel that goes through the dam to the power plant. And depending on how high the flow rate is, if there's so much water coming into the dam that they can't get it all through the power plant, sometimes they have to use these release gates. It's not like an emergency release gate, but it's an overflow release gate. All of the water that comes through the release gates doesn't generate electricity. They only have power generation ability for the water that's getting through this power plant. Here's a picture of the power plants themselves. There's a number of different turbines that are there. And let's watch what it looks like as water goes through the release gates, because they had a big event a couple of years ago, and they posted video online of what it looked like for water to be coming out of the spillways. And if we're patient, we'll get to view that interesting footage. Wait for it. Now this clip is 9 minutes long. Let's go through the calculations to see what the velocity actually is. So it was a special thing when they were using this for public, so that's why South Dakota Public Broadcasting put 9 minutes online. Well, let's check out this other link, because frankly I don't remember what the other link is. We also have this one. treasure dude. Takeaway from that video. How fast though? What's the velocity through those gates? Well, how could we measure the velocity through the gates? We could use a stagnation tube. Remember when we talked about stagnation tubes? So how would a stagnation tube work there? You'd get maybe a PVC pipe or something, and you're standing on the edge, and if you put the PVC pipe down in, so here's the jet of water coming out. If you put the PVC pipe down in like this, then the water level will rise to a certain height, and that certain height is dictated by the velocity of the flow. That would be one way of doing it, but it would have to be, for as fast as that water's moving, it would have to be a really big PVC pipe. It would probably be just awkward, and you'd put it in and it would shatter the pipe. It would just break right out of your hands. So that wouldn't work. So what's the upgrade from the stagnation tube that we talked about? What's that? Pitot tube, right. So the pitot tube is the one that, instead of venting to the atmosphere, the pitot tube is the one that has an interior opening to capture the stagnation pressure, and then it has an opening. So here's the opening at 1, here's the opening at 2, and then it's connected to a gauge that says what's the pressure on a differential basis. And so the pitot tube, we could actually use a pitot tube, put it down in there, and then measure what's the difference in pressure between 1 and 2. And then, using the formulas that were presented last time, we could measure the velocity that way. Another instrument that's sometimes used is, it looks like a box on top that has a little gauge on it, and then on the side is basically a little propeller. And you put it down in, and how quick that little propeller is spinning tells you the velocity of the water. But none of those are going to work for something that's as fast moving as this water is. So let's take a look at it another way. We can use the continuity relationships. What the continuity relationship says is that if you've got a pipe, then what goes in to the pipe has to come out of the pipe. And so if you've got a flow rate in, it's going to be the same as the flow rate out of the pipe. And flow rate can be calculated by the area of the pipe at the inlet times the velocity of the pipe at the inlet, and that's going to be equal to the area of the pipe at the outlet times the velocity of the pipe at the outlet. So let's look at some of the given data on this one. It's June 2011, and it was just heavy rains for days and days at a time that made it necessary to release 160,000 CFS through the dam. The maximum they can get through the power plant is 50,000 CFS. And usually the power plant has more than enough capacity to pass all the water that's coming in to the dam. So it's a pretty rare thing that you've got so much flow that you've got to put it through the spillway. And in this case, it's more than double the flow that's going through the power plant is going to go through the spillway release gates. Okay, so our total flow, Q total, is 110,000 CFS, cubic feet per second. So if there are 6 of the gates, then the flow rate through each gate is 110,000 cubic feet per second divided by 6. That means that there's 18,333 cubic feet per second going through each of those 6 gates. Why do you think it's important for us to know the diameter of the release gates? 19 feet. They didn't look like 19 feet in diameter, but that's the specifications I found, is 19 feet in diameter. Why do we need the diameter? It's because we're going to have to find the area of the outlet. What we know so far is the Q that's coming in. So we were told that the Q in for each of these gates is 18,333 cubic feet of water in each second is going to go through there. Now, the area is pi d squared divided by 4. Okay, and we have the diameter given as 19 feet. So the area of the pipe, pi times 19 feet squared divided by 4. So the area is 283.5 square feet. Any questions so far? Okay, well, V is Q divided by A. And you had to do this same formula on the flow visualization lab. Do you remember when you were trying to calculate the Reynolds number of the flow through that little tube? You knew what the flow rate was because you'd used the stopwatch and you'd used, we use a volumetric flask for that one, graduated cylinder. Anyways, you knew a certain volume, you knew a certain time, so you knew the flow rate, and you knew the diameter of that tube. So you've applied this formula before. In this case, we've got 18,333 cubic feet per second, and the cross-sectional area is 283.5 square feet. So if we look at the units, we see we're going to get feet per second, and that's what we need for velocity, so the formula is correct. 64.5 feet per second. So if I did jump in, it would propel me 64.7 feet downstream in the first second that I was in the water. All right. So that's the water velocity through the gates. That's a lot of water. You know, just to give you an idea of what's fast and what's slow, usually we would say that water going through a pipe, if it's going 10 feet per second, that's pretty fast. And so in this case, that's 6 times faster than what we would ordinarily say is, yeah, that's moving pretty fast at 10 feet per second. You know, in a pressurized pipe, 10 feet per second is fast. In an open channel, like what we saw, if the concrete isn't very nicely constructed, if the contractor wasn't doing their job, and if it's not designed to withstand scour, it will cause cavitation and erosion, and this water could not only scour the stream and the soil that's downstream, but it could also destroy the concrete itself. And so spillways like this, overflow spillways, are very carefully designed and modeled in advance because they want to know exactly how it's going to behave, because you know, during an event like this is the last time that you want your spillway to fail, and that's when you need it the most. And so there's been a lot of research, especially since the early 80s, when a gigantic dam almost did fail because during a wet weather event they were sending water through the overflow spillways, and there was cavitation that caused an enormous amount of erosion through that dam. Where did I put the... All right. Any questions on this example? The heart of Chapter 5 is mass balance. It's applying the principles of volumetric flow rate. And what this diagram is showing is that the volumetric flow rate, which has units of cubic meters per second, is simply the product of the average velocity through the pipe and the cross-sectional area. Now, V here has a line above it, and that means the average velocity. And what it is a recognition of the fact that the velocity through a pipe isn't always the same velocity. In reality, you'd have a velocity profile. But if you're taking the average velocity, you simply all you have to do is multiply them together. The mass flow rate has different units. We're talking kilograms per second. And so if you have a volumetric flow rate and multiply that by the density of the liquid, then you have the mass flow rate. Mass flow rate is going to be really important when we get to chapter 6. This m dot means how many kilograms per second of the liquid is moving through the control surfaces. And the reason why it's important in chapter 6 is we're going to be doing problems related to momentum and calculating forces as jets are discharged. And that's a whole different set of questions that we could do on this Oahe Dam, is how much concrete has to be in place in order to hold that pipe steady. Because if you've ever watched a fireman with a hose, you know, they have to have several people holding onto the hose or else it'll go totally wild and spray all over the place. And so what we were seeing, so much force is being generated when you discharge a liquid at a really high velocity like that. And it's related to the mass flow rate. So the continuity approach says that the study that you're doing is through a control volume. And in the case of this Oahe Reservoir, our control volume is the reservoir itself. We're keeping track of the flow rate in and looking at the flow rate out. And the difference between the two is related to an accumulation. The water levels will either rise or fall depending on if in is greater than out. Oh, here it is. So the relationship between these two equations is just that if you have volumetric flow rate, Q, multiplied by the density of the fluid, then that gives you the mass flow rate. And this works whether it's a gas or a liquid. This looks like the same diagram, but it's a little different. In this one, it looks like a cylinder is moving through the pipe. See how the face of this, the front face of the cylinder is just flat. This next diagram is a little different. It looks like a bullet that's going through there. And what that bullet is representing is a velocity profile. If I was just going to do a cross-sectional view, this is the middle of the pipe. What it shows is that the velocity is highest at the middle, and at the edge of the pipe, the velocity is 0. Because the water or the gas, whatever this liquid is that's moving this way, in general terms, it can't have a velocity that just slips over the surface. This is a frictional surface here, and this fluid that we're working with is viscous. It has some resistance to shear stress. And so there's the no slip condition. The no slip condition means that water can't slip in a frictionless way across a surface. But the interaction between the liquid and the conduit that it's flowing through, the conduit applies a resistance to flow in the opposite direction. And so that's why the velocity is high at the center of the pipe, is because the center of the pipe is the furthest away the liquid gets from that surface that's resisting movement. And so the further away the liquid is from where the friction is, the faster it's able to go. So what we have in this diagram is a three-dimensional isometric view of a velocity distribution, similar to this cross-sectional view. And what you'll see is that this time they've broken the surface up into little differential areas, dA. So just consider what's the velocity at this one little area. And if you integrate that differential velocity over all of the areas, if you looked at all the different pieces that make up that surface, then you can find the volumetric flow rate. So now there's no V bar in this formula. In the previous formula that we were looking at, it said that flow rate, the volumetric flow rate is V bar times area, where V bar means the average. In this one, it's not the average velocity, it's the velocity at every single little point multiplied by the area of that point, and that would give you the volumetric flow rate if you consider all of the elements together. And so in a like manner, the mass flow rate is the volumetric flow rate times the density of the liquid. So the cause of the velocity distribution is resistance to flow, or pipe friction, at the edge of the material. Here's probably a better drawing than I can do of different velocity profiles. The one on top is laminar flow. And when conditions are laminar, the velocity profile is actually pretty regular and predictable. The centerline velocity in laminar flow is double the average velocity. But when the flow is turbulent, there's quite a bit of random behavior inside of the flow. And as the water goes through the pipe in turbulent flow, you'll remember that when we were visualizing the injection of the dye during turbulent flow, sometimes the dye would be together, then it would all go in one place, and it would start spreading out. And so there's not just movement sideways in turbulent flow, but the flow is also moving this way, and it may reflect off of the side of the wall, and some of it's going here. And every particle has its own individual flow path. This particle may be moving all over the place as it's finally making its way to the right. Once the flow gets above a Reynolds number of 4,000, then the velocity profile changes. What looked like a nice bullet-shaped parabolic here where the centerline velocity is double the average gets to the point to where the average velocity is pretty close to the velocity at any particular point. In this drawing, U bar means the average velocity. And what this U is it means U for this particular location in the pipe. So sometimes it's less than the average velocity, sometimes it's more than the average velocity, but you could take an average over the entire area of what all the different velocities are, and the centerline velocity is going to be approximately the same as the mean velocity, whereas here the centerline velocity is twice the mean velocity. All right, I'd like you to try out the continuity relationship here. You're given a mass flow rate and a pipe diameter and the density of the fluid. And so what I'd like you to try calculating is the mean velocity of the liquid as it flows through the pipe, and also the volumetric flow rate. You've got the mass flow rate, you need the volumetric flow rate, and also calculate the velocity. Go ahead and work with a partner on this, work individually. Either one's fine, but I'll give you a head start on that, and then we'll start putting the solution on the whiteboard. We've got the diameter, so we can calculate the cross-sectional area of the pipe. Cross-sectional area is 0.196 square meters. The definition of the mass flow rate is the density times the area times the average velocity. So if we just rearrange that equation to solve for the average velocity, it's the mass flow rate divided by the density times area. And we know that the velocity ultimately should have units of length per time. So everything's going to have to cancel out for that to happen. We've got 550 kilograms per second, and are dividing that by the density, which is kilograms per cubic meter. So the kilograms unit goes away. We've got meters cubed in the denominator due to the density, and then the area, meters squared. So that's going to leave us with meters in the denominator, which then, because it's in the denominator of the denominator, becomes numerator. So our velocity is 3.295 meters per second. And then if we just substitute that into the volumetric flow rate equation, we find out that the volumetric flow rate is 0.647 cubic meters per second. Pretty easy stuff, right? Any questions about this one? All right. So just with this, I mean, this is a chapter with one idea, and that's it. You know, volumetric flow rate. So you can really start digging into that homework at this point, even just with the very few examples we've looked at so far. Let's talk about the theory a little bit more, though. Let's dig into the details of what this control volume approach is. The control volume approach says, what if there's a pipe? And you can see from the drawing here it's a bent pipe. And they did that on purpose just to illustrate the fact that it's okay if the flow velocity, if the flow is changing direction, and if the pipe diameter is changing, we can still use this method. This method isn't only applicable to like a horizontal pipe that has a constant diameter. This method handles any situation we can throw at it. There is a control surface, which is the outside of a control volume. This is a cross-sectional view of a pipe, and it's a circular pipe. And the control volume is like a sort of a misshapen cylinder. It's got a little bit of a bend in it. And the outside of that cylinder is the control surface. The system, there's a couple of important definitions that you need to be acquainted with. The system is the particles itself that's going to be flowing through this imaginary control volume. And for it to be a system, it has to be a continuously connected group of particles. The system can't be separated into two different groups when we apply the control volume approach like we're going to. The control volume itself, it can change its location, its position and shape can change over time, it can rotate. It's just an imaginary, object which the outside surface is bounded by this control surface. And the reason why we've come up with this imaginary object is it's just a unit of accounting. We're going to look at what flows into this imaginary control volume, what flows out, and sometimes there's an opportunity for accumulation inside the control volume. Not in the case of this pipe. There's no place that water can be stored when it flows in. If it flows in, it has to flow out. Sometimes, though, we'll put a storage tank in between location 1 and location 2. Like I've mentioned before, the control surface, abbreviated CS, is just the outside surface of the control volume. So here's the application of how the control volume works. What we're looking at is a tank that's connected to an inlet pipe and an outlet pipe. And we're looking at this tank at two different times. The picture at the left is what the tank looked like at time t, and the picture on the right is the same tank just a little while later at time t plus delta t. There's two different liquids here. There is a dark blue liquid, which we could think of, maybe it's oil and it's surrounded by a different liquid, or maybe it's water that has a tracer injected to it. But the system is just this dark blue water here that's representing a certain amount of particles that are being tracked over time. So look at where the system is at time t, and now look at where the system is at time t plus delta t. Now, I know it's not very obvious, but does it look like the liquid surface is the same in the two tanks, or does it look like it's different? Looks like this one on the right's a little bit lower. I agree. Now, what's the other difference is look at how long this is compared to how long that is. The one on the right, where the system is in the outflow section of the tank, through that outflow pipe, there's more of the system in the outflow pipe. And that's why the liquid level is lower on the tank on the right, is that more of the system is exited the storage area, this control volume that bounds the tank. More of the system has flowed out of the control volume. So what we'd say is between time t and time t plus delta t, the flow out was bigger than the flow in, and that's why the liquid level decreased. So just to summarize, when the liquid comes into the tank, there's two options for where it goes. It can either be stored in the tank or it can exit the tank. Those are the only two choices. The system, meaning the number of particles that are under study, that we're analyzing a certain number of water molecules or oil molecules, the system doesn't change, but the location in space changes over time. this big concept of studying a control volume can be broken down into a formula that is deceptively simple, and that is accumulation is equal to in minus out. And when I teach environmental engineering, I'll write this formula on the board 7, 8, 10 times a semester. And like before I write this on the board, we'll be looking at a problem that seems so complicated and unsolvable. It just seems like baffling. And then I'll write this simple formula on the board, and instantly it's obvious what you have to do to solve the problem. That's like the power behind the control volume approach is just you need to do a mass balance or an energy balance or in some cases a momentum balance. It's just that you can't destroy mass, and so you move it around in different places. And in this illustration, what it's showing is that the system, which is the mass that we're considering, it comes into the control volume, and it can either go out of the control volume or it can stay in the control volume, meaning it can be stored in the tank. And those are the only choices. And so if we want to know how much water is in the tank at a certain time, all we have to do is find out what was the water level in the tank at the last time increment, and how did it change during the increment. Was there a positive accumulation, meaning that the water level got deeper, or was there a negative accumulation, meaning that the water level fell? And the only reason there would be a negative accumulation was if out was bigger than in. And vice versa, if in is bigger than out, there will be a net positive accumulation and the liquid level will increase over time. So in symbolic language, what it says is that the mass of the system at time t is how much is in the control volume and the amount that's in the inflow pipe. And then at time t plus delta t, it was the amount that was in the control volume and then how much was in the outflow pipe. So the system changed its location over time. And the net accumulation in the control volume, the change in mass that was inside this control volume, is accounted for by the flow in and the flow out. So the change in mass over time is related to the mass flow rate in and the mass flow rate out. Remember m dot, mass flow rate, the definition of that is it's just the density of the liquid times the volumetric flow rate, where the volumetric flow rate is the area times the average velocity. There's a few more definitions in the textbook that I hope that you've seen already as you're reading in the textbook, but we'll just identify that some properties of fluid are related to how much of it there is, how much fluid is present. And some properties are independent of the amount of fluid that's present. So let's start with the easy ones, the intensive properties. An intensive property of a fluid means it doesn't matter how much is actually there. So the color of a fluid is a good example of something that it doesn't matter if there's a little bit of a fluid or a lot of the fluid, it's going to have the same color. The water in the bench on the right that's tinted blue, because remember we were injecting all that dye into it during the flow visualization experiment, it has that same color of blue whether there's a liter of it or 20 liters of it. You know, maybe it's more noticeable if there's more water, but it has the same color. That liquid has the same viscosity. It doesn't matter what mass is present. Intensive properties stay the same. But there are some properties that fluids have that vary as a function of how much of it there is. And so one that's obvious is mass. You know, the mass of the fluid is related to how much mass is present. That's obvious. But other ones that are less obvious is the momentum of the fluid depends on how much mass that is present in the fluid in the system. How big is the system is going to dictate the amount of momentum. And so those big gigantic pipes that we saw at the beginning of class, the amount of momentum that it's exerting to the surrounding concrete that holds those pipes in place is related to the mass that's flowing through the pipes themselves. And the amount of energy that can be generated by the power plant is a function of the mass flow rate of the water. So that's what we call extensive properties, are fluid properties that depend on how much of the mass is present. When the fluid is moving around and we do this accounting procedure of tracking the flow into the control volume through the control surface and the flow out of the control volume through the control surface, the properties are transported along with the fluid. So the water exits the reservoir, it's taking energy with it because that is an extensive property, and the fluid property, the energy that's in that fast-moving water that's pressurized, gets moved around through the control surface. This is what we call the Reynolds transport theorem, and this is just a really fancy, complicated way of describing this simple principle. Accumulation is in minus out. What it says, we can break Reynolds transport theorem into two different terms. There's a storage term and a transport term. What the storage term says is consider that tank that we were just looking at a minute ago, the tank where liquid is accumulating, flowing in and flowing out. Okay, so take this tank for instance, and we're going to have control volumes and control surfaces. So here's our control surface. It's the outside of the control volume, and then the control volume is the interior part that is within the control surface. If you keep track of the flow through the control surfaces, the transport is the in and the out. So you can write in the margins there of your paper, transport is in and out. So it's the right-hand side of this very simple accumulation equals in minus out. So how do we read this language here? It's saying take the integral through the control surfaces. That means look at the velocity at every little part of this pipe, because we can't just assume it's going to have some average velocity, but there's a variety of velocities possible, and if you integrate over the entire circular opening of this pipe and consider the outlet as well, you take the in and the out, multiply it by the velocity at each point and the dA, differential cross-sectional area, multiply that by the density of the fluid, then that will tell you the mass flow rate in versus the mass flow rate out. And you'll notice that this whole equation is on the basis of mass, dm dt, the change of mass of the system over time. The other term, the storage term, is related to accumulation. So storage is what I've written as accumulation. So that is, does the water level go up or does the water level go down? And it's dictated by the difference between in and out. So the storage term says you multiply the density of the liquid by the change in volume. And that's going to be, over time, a mass flow rate as well. The change in volume over time multiplied by the density gives you another mass flow rate, which will have units of mass per unit time, like kilograms per second. Most of the time, mass is neither created nor destroyed. If there's some sort of a chemical reaction and we're only looking at a mass balance of the product of the chemical reaction, or if it's a nuclear reaction, there will be mass created or destroyed, because sometimes we only look at one component of the reaction. But we're ignoring chemical reactions and nuclear reactions in the fluid mechanics, and we're just looking at the movement of mass rather than its creation. And so this Reynolds transport theorem is simplified by saying, consider that this whole term is zero. The change of mass of the system over time. We're not going to create or destroy mass, and so the left-hand side of the equation is zero, and then that simplifies, the Reynolds transport theorem simplifies to this. And it's interpreted as the change of mass in the control volume over time is related to the mass flow rate in minus the mass flow rate out. So this is the technical way of expressing what I've written here conceptually is just accumulation is in minus out. Well, it's saying the accumulation of mass over time So that's more detailed than what I wrote. This is saying the accumulation of mass inside the control volume over time is equal to the mass flow rate into the control volume through the control surfaces minus the mass flow rate out of the control volume through the control surfaces. Okay. Any questions about Reynolds transport theorem? All right, so I had a request to go over one of the homework problems, and we've got a little bit of time remaining, so I'm happy to do that. The question was about problem 439, which is that cylinder that was accelerating upwards. All right. That homework problem, there was a piston that's accelerating up. The acceleration in the z direction is upward, and what do they say the acceleration is? Oh, that's what you need to find is the acceleration. All right, so that's the unknown. The two locations where we know things, we know here and here the pressures. It's given that the pressure at 2 is 0, and the pressure at 1 is given as, they say a certain psi, right? Oh, there it is, 8 psi. Okay, so we have to convert that into pounds per square foot. So if we multiply 144 inches squared per foot squared, that tells us that the pressure at 1 is 1152 pounds of force per square foot. This is obviously an Euler's equation problem. You've got an accelerating fluid. We want to know the change in pressure between 2 points. It's given that the depth, the delta z, is 10 feet. Okay, so Euler's equation, when we write it out, is P2 plus gamma Z2 minus P1 minus gamma Z1 is equal to negative delta Z, density, acceleration in Z. So this distance term is a delta Z because the acceleration is vertical. Sometimes we write delta X when it's a horizontal acceleration, but here it's delta Z because of the vertical plane being how it's accelerated. Let's let Z1 is equal to 0, Z2 is equal to 10 feet because we know the distance between 1 and 2, and then that's also going to give us that delta Z is 10 feet. Any questions so far with how this is getting set up? The pressure at 2 is 0 because it's at the surface there. We can rearrange all of this to solve in terms of A sub Z. It is P2 plus gamma Z2 minus P1 plus gamma Z1 divided by negative delta Z times the density. That's just isolating the acceleration variable from the rest of the equation. The pressure at 2 is 0 plus the liquid here being water has a density, a unit weight rather, of 62.4 pounds of force per cubic foot. And Z2 is 10 feet minus P1, which is known as 1152 pounds of force per square foot, plus 0 because the Z1 term is 0. And we divide that by negative 10 feet times the density, which is 1.94 slugs per cubic foot. And that gives us the acceleration in z is 27.2 feet per second squared. All right. Any questions about that homework problem that you've just got back? Yeah, the seconds. It's because you actually, well, you come up with seconds because if you you need them to be there because you have got slugs per cubic foot and you're dividing it by the pounds. So, right, the slug is a pound. A pound is a slug times foot per second squared. Yeah. Yeah. Okay, so that's it for this time. I'll see you next Tuesday.